Hello. So in this short video, I'm going to talk about categorical distributions, how they're used in NLP. So basically, what they are, how they're used in in NLP, and I'm going to talk about one way to represent them and to estimate the parameters for categorical distributions. So let's start with precisely the categorical distribution. So this first part, you can call it a recap if you like. So the categorical distribution is the probability distribution of a discrete random variable, taking on outcomes in a countably finite set of k categories. So you have a set of k categories. These categories could be named. And for example, if they're colors, it could be blue, red, white, black, and so on. And you have a random variable that takes on outcomes in this set. Now we denote a categorical random variable over these k categories as categorical, spelled out like that, theta 1 all the way to theta k, or categorical theta 1k for short. So if I present you with this, a categorical theta 1 through k, I'm essentially saying you have a categorical random variable, it's distributed, its outcomes are in a set of k elements, and these quantities, theta 1 through theta k, are called the parameters of the categorical variable. Essentially, they are the parameters that specify the categorical probability mass function, or PMF for short. There are certain conditions on these parameters. Each parameter is constrained to being between 0 and 1. For any of the outcomes. This is a short way to write j in 1 through k. Okay, so these are the same. And if you add up all the categorical parameters, you should get exactly 1. So if you have a random variable, capital C, and I say it distributes as a categorical random variable with parameters theta 1 through theta k, then what I mean to say is that C is a random variable. It may take on values in the set 1 to k, and the probability with which C takes on a certain j is the jth theta. Okay, and another way to denote this is to put the C as a subscript here. I use one or the other depending on how much space I have on the slide. Okay. One side note, if we think of theta 1 through k as a vector, since it's a fixed dimensionality, we can denote theta as a vector. It's basically, well, vectors are columns, so the transpose of this row vector. It's a point in a specific space that we denote with this symbol, this triangle with the subscript k minus 1. This thing here, it goes by the name of probability simplex. It is a subset of the k-dimensional real coordinate space. And every point in it is a k-dimensional vector that complies with these two constraints. Okay, so that's just a curiosity. If you want to say this in a very short way, you can basically write this. Now, we can visualize a categorical PMF as a bar plot. And I'll show you with an example. So if C is categorical with probabilities 0.7, 0.05, 0.25, see that it adds up to 1. And I use it to represent a traffic light, the state of a traffic light, and I assume the coordinates are associated with the outcomes red, yellow, and green in this order. Then I can view the PMF as something like this: red, yellow, green. So here I have the sample space, some sort of calligraphic C. And here I have probability. And this is 0.75, this is 0.05, and this is 0.25. This is the PMF. I often use the category as an index. So if you see theta red, I mean theta 1. And if I see theta yellow, I mean theta 2, and theta green, then I mean theta 3. Of course, the mapping between categories and their indices has to be one-to-one, and it's up to the designer. The order doesn't really matter as long as it's consistent. So this is typically going to be clear in context or for the application you're working with. All right, so in NLP, we'll often use this distribution. It's everywhere in NLP. Let me put a title here: Categorical distribution in NLP. It pops up all the time to model categories such as, words, document classes, topics like sports, news, syntactic classes like something is a verb, something is a noun, something is a pronoun, and so on, and many other things. For example, we might say that in a certain application, this is a categorical distribution for sentiment, where I assume sentiment is categorical, and I have 3 levels: negative, neutral, and positive. I might also have in a different context, I might say, well, W is categorical with parameters theta 1 through theta v. This time I'm not going to invent numerical numbers, I'm just going to name them with variables, theta 1 to theta v. So I have v possibilities for this random variable W, and it's to capture words. Right, so v here being my vocabulary size, so perhaps theta 1 is corresponds to the probability of drawing a the. Maybe theta 102 corresponds to the probability of drawing a dog, maybe, and so on and so forth. Now, more often than not, what we really deal with is the distribution of a categorical variable in context. And those are the conditional probability distributions, or CPD for short. So for example, we might be interested in the distribution of words given that we are talking about a document that is overall positive. And that is a categorical random variable with parameters theta positive 1 through theta positive v. And I'm going to explain this notation a little bit better. So I'm using the symbol theta superscript positive to denote all values theta 1 through theta v that are specific to the condition that the random variable c has outcome positive, as opposed to, for example, the neutral case. Or even the negative case. So see that to specify the distribution of the random variable w, I need to know the class. The class is positive. Okay, so this is the distribution. Those v numbers specific to the positive case will specify the PMF of this random variable. In a different situation where c is actually neutral, then other v numbers, these ones, the ones that are specific to the neutral case, will give me the PMF. And in a different situation where c in fact is negative, I have another collection of v numbers which specify the PMF of my categorical random variable. All right? This way to denote them already give you a hint at what we call a tabular CPD. So conditional probability distributions of a given kind, for example, of the kind word given class, they can be visualized and in fact represented in a computer program, for example, or stored as a table. Well, the PMF of these objects, the PMFs that completely prescribe this, the set of categorical, the set of conditional probability distributions of the kind W given C, can be stored in a table. The table could be visualized as something like this. So here you have the outcomes of C, here you have the outcomes of W, and maybe you have negative, neutral, and positive. Right, maybe this is the first, the second, the third coordinate. And here you have, all the words in English. So for example, A and the sum, and it goes on, right? And you have, somewhere a cat, somewhere a dog. It goes all the way to the last word in the vocabulary. And then maybe these are the indices of the coordinates. And the complete table then would be pretty large. The number of classes times the number of words. This is the so-called tabular representation. Each row is identified with a parameter vector. So for example, here I call this negative, neutral, and positive. And if you go here somewhere, what you have is the theta corresponding to a negative C and coordinate for or word sum. Right, and then here you have theta positive, outcome dog. Right, and what we know about these numbers, well, they are all between 0 and 1. And if you were to sum any one row, you would obtain a total of 1. And they add up to 1 row-wise in this representation. Okay, so these are tabular CPDs, very common objects in models like the naive Bayes classifier and n-gram language models, which we'll cover in class. I also want to talk about how to estimate the numerical values of the parameters. It's easy to talk about them as variables. At one point, we want to put numbers in them. So to estimate the numerical variable values of parameters, you need a criterion. And the criterion of choice in this course is maximum likelihood estimation, or MLE for short. And it goes about like this. First, you gather data. And a data set basically is a bunch of observations of the relevant variables. So for me here, let's go with a class and a word, and maybe you have n such pairs. So you've observed class word pairs, and once you have that, then you instantiate a likelihood function. Remember that our model of the data here is that for any w in a given context, we draw a specific outcome with probability theta c1 through v. Right, so the probability of drawing w equals a small w, given that c is some small c, is theta c coordinate w. So I'll write some examples. The probability that w is a dog for a positive class in a positive document is the vector specific to the positive document's coordinate dog. Right, and w is a dog given that the document is neutral, and this is the theta specific to neutral documents coordinate dog, so it's a different theta. Right, and a likelihood function for a data set, in fact we're going to use the log of the likelihood function, can be written like this. So if I denote by boldface theta the collection of all parameters, so basically the entire table, the log likelihood function is a function of those parameters given a data set, and because of IID assumptions, it boils down to the logarithm of the probability that our model assigns to each of the observed outcomes. So in this case, we're going to have for each of the contexts, we have a parameter for the word, and a logarithm of that probability is added together. They are added together. That makes the log likelihood function of the log likelihood of the parameter value. And we can find an optimum of this curve. So we look for a local or global, depending on the kind of optimization we do, optimum of this function. And for the tabular model, this has an exact solution, and that solution is count how many times you've observed a certain class occurring with a certain word, and divide that by some count how many times you observe that same class occurring with any arbitrary word in the vocabulary of few words that you know. To prove this result, you need to know a little bit of calculus, a little bit of Lagrange relaxation, and then you could actually find the optimum choice of theta, and you would see that it corresponds to this formula here at the bottom. Right, so I think the very last thing we want to do is to work through a complete example. So I'm going to give you a data set with, various class word pairs. We have positive dog, positive cat, and I'm going to pretend that my entire vocabulary has size 3. I only know dogs, cats, and birds. Maybe I have another negative cat. I don't know why they seem to be negative about cats in these documents, and well, occasionally about dogs. And I have neutral documents about dogs, and neutral documents about birds, and more neutral documents about birds. And my entire data set has 9 observations. Right, and I'm gonna assume a categorical model of words given the classes of the documents they occurred. It's going to be a categorical model represented in a tabular manner. Therefore, for each condition, I'm going to have V parameters. Well, my V is 3, so I can spell this out. This, in fact, boils down to a table where I have negative, neutral, positive rows. So these are my values of C, and I have only 1, 2, 3 words in the vocabulary. I have dog, I have cat, and I have bird, and these are my parameters essentially. So all 3 negative parameters, all 3 neutral parameters. I'm spelling this out just once. And all 3 neutral parameters should include a parameter for bird. We have all positive parameters. Right? And what I know about them is that they are between 0 and 1, and if I sum them row-wise, this gets to 1. And I can use this data set and this model definition to obtain a maximum likelihood estimate of theta, no matter the class, no matter the word. And for that, I just count the joint occurrences of class and words for small c, small w, and I divide by joint occurrences of class and words for small c, same small c, and any arbitrary word O in the set of known words. And my set of known words, again, is just dog, cat, and bird. Alright, so these are my words. So imagine a calligraphic W, and my classes calligraphic C would be positive, negative, neutral. I know in set notation order doesn't make too much sense, but just to be consistent with, I'm sorry, I deleted the wrong thing. To be consistent with the order I was presenting you earlier, I will list them like this. Okay, so let's compute the parameter values. So I'm gonna bring my formula here to the side, and essentially I have theta negative, theta neutral, and theta positive, right? And I have 3 values in each case. And they are, well, for dog, cat, and bird, they're based on this data. So let's count. For the negative class, I'm going to use a highlighter here. I have 3 documents that are relevant. I have 1 occurrence of the word dog out of 3 occurrences of negative classes. I have 2 occurrences of the word cat out of 3 occurrences of the negative class. And I have 0 occurrences of bird out of 3 occurrences of the negative class. So these are my maximum likelihood estimates. Let's go for neutral, maybe with this color. And let me highlight the neutral stuff. We have again 3 occurrences, and I have 1 dog out of 3 occurrences, and I have 0 cats out of 3 occurrences, and I have 2 birds out of 3 occurrences. And last but not least, let's do the positive stuff. So let me highlight here the positive stuff. And I have 2 dogs out of 3 documents. I have 1 cat out of 3 positive documents, and I have no bird. And it is a coincidence that I have 3 of each. Okay, I chose a data set like that. I could have given you a data set with, I don't know, 6 or 7 positive documents and only 3 or 4 negative documents and only 1 or 2 neutral documents. This is it. This is a complete example. And a couple of implementation notes. We can implement these as a table indeed. The entire model is stored in a table. Often we use a sparse data structure, and then we do not actually represent the zeros. We only represent the outcome pairs for which, context outcome pairs for which probability is non-zero. Sometimes we use so-called smoothing techniques. You will hear more about them later. When we use smoothing techniques, then it's more convenient, oftentimes more convenient, to store the counts, at least the non-zero counts, as opposed to the probability values. Okay, so you would actually store counts. So imagine I can quickly make a count table. Let me copy this and paste it here on the side. I'll make it a bit smaller. A count table would just look like this. And you see, I would use a count table because whenever I need a probability, I can obtain all quantities from here. So if I'm smoothing functions, they interact with the counts the counts of the relevant outcomes in the observed data, in the training data. So if I ever needed to, for example, obtain a smooth probability for the masses in this vector, let me highlight it, this one, and maybe I'm smoothing by adding 0.1 count to every single event. Then if I ever need the probability of dog, I would know that it's 1 plus 0.1 divided by 1 plus 0.1 plus 2 plus 0.1 plus 0 plus 0.1, which then is essentially 1.1 divided by 3 plus 3 times 0.1, or 1.1 divided by 3.3, right? So this would give me the possibility to compute the probability, smooth it while performing that computation. And smoothing means reserving probability to unseen outcomes. And then you see that if I had to compute the probability, this was for dog. If I had to compute for bird, then that would be 0 plus 0.1 divided by 3.3. So you see that without storing these sparse outcomes, I would still be able to assign a probability to it, and I would be able to assign a probability to it efficiently. Okay, so that's the implementation note. We typically store these models or the parameters of this model using a table or a sparse matrix, and if there's no smoothing, it's okay to store the probabilities directly. If there is smoothing, it's often a better idea to store the counts. That's all.